So hello everyone, this is Dr. Nimish Kumar Srivastava in this video lecture series of optical communication, that is KEC 058. In our last lecture we was discussing about the optical source. We've gone through the various phenomena that is related to the optical sources, and we have discussed what are the types of optical sources, LEDs. In that too we have discussed two important configurations, that are edge emitting LEDs and the surface emitting LEDs. So now we are going to concentrate about some important parameters that is related to the LEDs, which is your internal quantum efficiency. So in this internal quantum efficiency, we have discussed, it is called as the ratio of radiative recombination to the total recombination that is occurring inside the material. So it is something given by RR and equals to the RR plus RNR. This is RNR is indicating, your RNR is indicating the non-radiative recombination. It is indicating non-radiative recombination, because we know that whenever a recombination is occurring, there will be a possibility of two things. It's not no material in this world can leads to 100% generation of this photons. Somehow there will be some non-radiative recombinations, right? So that's why in considering a total recombination, we have considered a radiative as well as the non-radiative recombinations. And this this lifetime is inversely related to the recombination rate. That means your radiative recombination rate is inversely proportional to the carrier lifetime, which leads to a radiative recombinations, right? So in this way we can see that, because we know that RR equals to 1 upon tau R and RNR equals to 1 upon tau NR. So if you put these two values inside this first expression, then you will get tau NR upon tau R plus tau NR. So this is the most important expression that one have to keep in his mind when he is attempting the numericals in the optical communications, right? So that means tau NR upon tau R plus tau NR is the most important expression for the internal quantum efficiency, right? Now once we have discussed what is the internal quantum efficiency in terms of your the expressions. Now we have to just visualize what is the meaning of this internal quantum efficiency, right? If I am saying that my internal quantum efficiency having a value of 95%, then what is the meaning of that 95%? Its meaning is that out of the 100 photons that is incidenting on the electron in the conduction band, that 95% of that photon leads to a generation of a light. If I am saying that out of if I am saying the quantum efficiency of the LED is 20%, so what is the meaning? We are suppose that we are having 100 photons that is incidenting on the electron, and after that that electron is going to recombine with the holes. So means that out of 100 photons that is incidenting on the electrons, out of those 100, only 20% electron will leads to a recombination of electron hole pair into the radiative region. That's called as the quantum efficiency of something called as a quantum efficiency of a LED. Now once we got this quantum efficiency of the LED phenomena, that's a basic idea. Now the next thing is that we have to discuss the internal power, that is the power generated, optical power generated internally in the active region of the LED. So it's something given by formula which is equal to the P internal, although we are not deriving this formula because is the formula which is already given in all the books of optical communications, whether you are considering a senior or a Kaiser. All these book cover the derivation of this internal power that can be the optical power that can be generated internally in the active region of the LED. One can easily go through those different steps in order to get this concrete formula, that is P internal is equal to eta internal into I by Q into H nu. So this is the internal power which can be generated. So this is also another important formula. Apart from remembering this formula, one have to remember this formula also, that is the internal power generated by the LEDs. So this is the internal quantum efficiency. This is I by Q, where I is the current flowing through because of this electron hole pair recombinations internally, and this is the Q, this is the charge of the carrier, and this is the energy, that's the band gap energy, that is H nu. And if you are converting that frequency in terms of a wavelength, which we know that the nu is equal to C lambda, just put that expression nu is equal to C by that nu is equal to C lambda. In that case you will get the C is equal to nu lambda. In that case you will get the nu is equal to C by lambda, and this is the final expression that you will get. So both these expressions are very important related to the numericals. So one can directly get the numericals. They will give the different values, like what is the value of the wavelength at which your LED is used, and what is the that is a charge carrier that is flowing, which leads to a generation, which leads to a current through this LED, something given by I. Now is the injected current to the active region, and P internal is the internal optical power. Now the next thing is that, and the part that is associated with the LED is the external quantum efficiency. Apart from internal quantum efficiency, which we saw, it is a ratio of a radiative recombinations rate to the total recombination that is occurring in the LED. Now apart from that, the external quantum efficiency is something given by the ratio of number of photons emitted from the LED to the number of photons, or to the number of photons that is generated internally from the LEDs, that is number of photons emitted from the LED, and the ratio is equal, and the number of LED internally generated photon. So that is something given by the external quantum efficiency. Now apart from external quantum efficiency, we have to get that what is the light output that is coming from the LED. We have to just formalize that expression. So that is something given by this expression, that is P equals to eta external into P internal. What is P internal? It is the power which is generated internally from the active region of the LED, and this P is the actual power which is now emitted from the which is taken from the LED, right, which is something given by eta external into P internal, which is further simplified as P internal upon N1 into N1 plus 1 whole square. Now next thing is that about the LED is the modulation of the LED. Now what is the modulation of a LED? What if we are discussing this term of a modulation of LED, what is that? What is the meaning of behind this? Modulation means how fast we are turning on and off the LEDs is something called as the modulation of your LED. So the frequency response of this LED will depends on some criteria. What are those criteria is something that we will discuss in this slide. So that three different criteria is that doping level in the active regions. If we are doping that particular active regions, that means depletion regions very high, that if you are doping that depletion region very high, means that the carrier density will be maximum in that region. If you are doping it very low, in that case the carrier density inside that depletion region will be very less. So that doping level is the most important criteria, which is responsible for deciding the frequency response of the LED, and that too doping inside the active regions. Apart from that, the second point is the injected carrier lifetime. Whatever the carrier that is injected, its lifetime is very important. That means injected carrier lifetime in the recombination region. And then the final one is the parasitic capacitance of the LEDs. If you are talking about the parasitic capacitance of the LED, apart from this, the most important point is the junction capacitance. How a junction capacitance is related to a LEDs. Junction capacitance means that depletion region. That depletion region is going to decide the working of your LED. That means how fast it is working. Now, in this, the drive current, suppose that if the drive current of a LED is modulated at a frequency omega, well, then the output optical power of the device, how it's going to vary? It's going to vary by using a formula which is P of omega, which is equals to the P0 plus of under root of 1 plus omega tau I whole square. This omega tau I is the carrier lifetime in the recombination region, and this P0 is the power at a zero frequency. So with the help of this formula, you can easily find out the optical power output of the device. Apart from that, if one want to define the electrical bandwidth, then electrical bandwidth is something given by the formula 10 log ratio of 10 log P omega upon P0. P omega is the power at particular frequency and P0 is the power at zero frequency, and P is the electrical power and I is the electrical current. So it can also be related in terms of current. So if it is related in terms of current, it is something square, so that's why we are having a 20 log I omega upon I0. I omega is the carrier, that means it is the electrical current at which we are concentrating, that means at the cutoff frequency and at the zero frequency. Now this is the bandwidth related to the electrical, that related to the optical as well as the electrical. So in the case of electrical bandwidth, this is the electrical 3 dB point and this is the optical 3 dB point. So this is the figure that one have to keep in mind if it is describing the modulation bandwidth of the LEDs. So remember that modulation bandwidth is something concept which is taken from how fast we are turning on and off your LEDs. So that is something given by this expressions. So now once we got this information of LED, now the next part is that we know we have to develop the idea of a laser, right? We have discussed all the points related to the LEDs. What is LEDs? It's based upon the principle of a spontaneous emission, which is called as in which whenever a light is incidenting of the electron in the higher energy level, it will going to emit another photons, is something called as a stimulated emissions. Whereas in the case of spontaneous emissions, once light that the electron has absorbed the energy from the external energy, so it will move into the higher energy level, and after its carrier lifetime it will fall back into the stable state, that is the ground level, and while falling back from the higher to a lower energy state, it will emit a photons. It will going to emit a photon, which is the phenomena which is responsible for the LED. Now in the LED also we discussed that what are the important criteria, what are the important requirements of optical communications, so that a particular source can fall under the category of a good LEDs or a good laser. So in that case we have discussed various criteria also. Then we have discussed what is the main difference between LEDs and laser. LED is non-coherent, laser is coherent. So this important criteria is responsible for laser to be highly directional. If some laser source is highly directional, means that can efficiently couple the light into the optical fibers, that means especially into the single mode fiber. This LED is basically used in the area of a multi-mode fibers. where multiple modes, because the LED spectral width is large in comparison to your laser. So if spectral width is large, that means it will support multiple modes. So it can be used in the multi-mode optical fiber, whereas in the case of laser, used in a single mode optical fiber. Now, apart from that, LED is having a spectral width is in the range of around 60 to 80 nanometer, whereas laser is having a spectral width of around the 1 to 5 nanometers. That means they have a very narrow spectral width, which is very good if you are talking about the criteria with which we can decide whether this is falling under the category of a good source or not. Now, next thing is about the laser. In the laser, we will see what are the important phenomena that is associated with a laser. So, that important phenomena are, before moving into details about that important phenomena, we have to first understand about the basic phenomena which is responsible for this laser. So, the basic phenomena which is responsible for this laser is called as the stimulated emission. So, we will first discuss that as stimulated emission, although we have discussed that in our previous that discussion. So, but before moving into the details about the laser, first we have to recap that process. The first thing is that stimulated emission. We are having two energy level, E1 and E2, whose energy difference is exactly equals to the h nu, and we are having an electron in this region, that means into the excited state, into the higher energy level. So whenever your photon is incidenting on the electron, it's going to stimulate that electron, and electron will fall into the low energy state, which leads to a emission of a photon. So we got two coherent photons which is emitted from this this incident photons. This is called as a stimulated emission. This is called as a stimulated emissions. So, and this is very responsible for the laser action. So, what is laser? For giving you the brief idea about what is the basic phenomena that's going to occur inside the laser. What is this full form of this laser? Light amplification by stimulated emission of radiation. This is the full form of a laser, and from here got the name. If you take this LASE and R, so from here it got the name laser, right? So now after this, another important point is that what are the various phenomena that going to responsible for the working of this lasers. So after this important descriptions, we have to understand what are the different phenomena which is responsible for this laser. So in your laser, some important phenomena that are occurring. First is called as the population inversion. Second is called as a stimulated emission. And the last one is called as the positive feedback. All these phenomena, they are going to combine and give you the operation of a laser. So all these phenomena going to occur inside the laser. Now the first important thing is that the population inversion. Why the name given the population inversion? Initially in the thermal equilibrium we know that the most of the electron are going to reside in the valence band. So and the conduction band is having a very less number of electrons. So in a population regions somehow we are pumping the electrons, and that electron will move into the conduction band. So now maximum electron will reside in the conduction band. That's why it is called as the population inversion, because we know that the initial at the ground level at the equilibrium case, most of the electron is in the valence band, but by pumping the energy, we are providing more energy, you are exciting that electron to move into the high energy level, and now you are reversing the number of electrons initially in which it is case was residing. Initially it was residing in the valence band, now it is residing in the conduction band. That's why it is called as a population inversion. Once most of the electron is in the conduction band, now you can efficiently utilize this stimulated emission process, because if maximum number of electron is present in the conduction band, then by the process of stimulated emission you are going to impinge a photon on the electron which is already in the excited state. This electron will fall back into the ground state and recombine with the holes. So while this recombination process, with the help of this recombination process, is going to emit the photons. So maximum number of electron going to recombine, give you the more number of photons. And the last one is called as a positive feedback. In this positive feedback, we are actually providing a two mirror at the two ends of the laser. So this is called as a laser having a cavity length of L. So if a photon is emitted, suppose that if a photon is emitted and they are moving in this direction, this photon going to be reflected from here, and this two photon again going to strike the electrons, two electrons, which will again generates the four photons. So in this way there is a positive feedbacks that we are providing into the laser. This positive feedback going to increase the number of photons that is emitted. So once we have increased the number of photons that is emitted, means that we are increasing the power which can be emitted from optical power which can be emitted from the laser. That means it's going to be highly directional, it is going to be highly coherent. So this is all three process that one have to remember if in order to move into the details of the laser. That means first one is a population inversion, second is the stimulated emission, and the last one is called as a positive feedback. So all these phenomena one have to remember in order to study the laser. In our next video lecture we will see what are the types of laser. Once we got this information about the laser, now next thing is that what are the types of laser. In that we will study some types, basic types. Those basic types are, first is your distributed Fabry-Perot laser. Fabry-Perot laser. Another is a distributed feedback laser. And the last one is called as a vertical cavity surface emitting, vertical cavity surface emitting laser diode, right? So all these laser we will see in details in our next video lecture. Out of these things, the Fabry-Perot is the most basic form, which we have already discussed in the form of a cavity when we have discussed the optical ring resonator, something like optical ring cavity. In that we have taken the two mirrors at the two facets of this laser active length, and that leads to a positive feedback. So we will see in details about this, the most basic form, Fabry-Perot, and then after that we will see how we can get a more narrowed spectral with the help of distributed feedback, and then finally we will see the most efficient form of a laser, that is called as a VC SEL, that means vertical cavity surface emitting laser diode. So that's all for today. We will see in our next video lecture the basic categories of all these lasers.